In this second lecture on the theory of extensive measurement, I want to do two major things. One is to complete the outline of the proof of the theorem for a closed extensive system that I was discussing last time. And second, in the second half hour, to describe a theorem that generalizes this one by relaxing the closure property of the operation. You recall the theorem that we're interested in begins with a system that consists of a set of binary relation and a closed binary operation. And it asserts that that structure has a homomorphism into the positive additive reals if and only if the following five conditions are satisfied. That the ordering is a weak order, the operation is weakly associative, that the ordering and operation satisfy the property of monotonicity, that is, adding the same element to both sides of an inequality does not alter the inequality, and that's whether you do it from the right or the left. The fourth property is the Archimedean property cast in a slightly peculiar form, saying that if A is greater than B, then for some integer n copies of A concatenated with an arbitrary element C is at least as great as n copies, actually strictly greater, than n copies of B concatenated with an arbitrary but fixed element D. And positivity of the system says that if A is concatenated with B, that is something larger than A itself, or B for that matter. Now, we said last time that the proof of this is reduced to Holder's theorem, and what I'll be doing in this first half of this lecture is establishing that the nature of that reduction to Holder's theorem. Holder's theorem, you recall, begins with something a little bit different structure, namely an Archimedean ordered group. The O operation, instead of being what is called a semi-group operation as here, is a much stronger operation in the ordered group situation. It's a group operation. It's associative. There's an identity and an inverse. And the theorem asserts that such an Archimedean ordered group is isomorphic to a subgroup of the additive reals. Now, on the assumption that that is true, I will try to show you how this theorem is reduced to that one. Now, there's a hint of the general nature of the strategy in the form of this Archimedean axiom. You recall that I argued that this was a perfectly plausible form of the Archimedean condition if I were looking at differences. That somehow or another this is capturing the idea that the difference between A and B can be made sufficiently large by making replication so that I'm looking formally at n copies of A minus n copies of B, that can be made greater than the difference between D and C. If I had some understanding of what I meant by minus here, that's essentially what I am saying. Now that hints at the idea that the system that we're going to try to generate from this ought to have something to do with differences. And that is indeed what is introduced here in the first step of the proof. We introduce an idea of differences within the structure by looking at the Cartesian product of A with itself. So a pair AB in that Cartesian product can be thought of intuitively as the difference between A and B. And we'll define equivalence among these differences. AB difference is equivalent to the CD difference provided that A concatenated with D is equivalent to B concatenated with C. Now, we can see that is plausible if you have an additive representation. Let me put that down here. Suppose I had an additive representation, then this would look like phi of A plus phi of D equals phi of B plus phi of C, or rewriting phi of A minus phi of B is equal to phi of C minus phi of D. So this is saying that the difference in the representation of the AB pair is the same as the difference of the representation of the CD pair. So this seems like a very plausible way to define the equivalence of differences. Now, the next step in the proof is to prove that this relation, double squiggle, is in fact an equivalence relation. That is, that it is reflexive, symmetric, and transitive. That's not terribly difficult to do. Incidentally, the proof that I'm outlining is worked out in detail on pages 78 to 81 of the Foundations of Measurement. Now, having shown that it's an equivalence relation, one immediately jumps to working with the equivalence classes. And I'll denote by square bracket AB the equivalence class that includes the pair AB. And I'll let D stand for the set of all those equivalence classes. This is the usual notation for that, the Cartesian product modulo the equivalence relation. And I'll let P consist of those equivalence classes for which the A element is strictly larger than the B element. In other words, P represents the class of positive differences. Now, it's on this structure of equivalence classes that I'm going to define an operation and an ordering that will wind up being an Archimedean ordered group. So it's the differences that are going to have the group structure. Now, the definitions are as follows. The operation holding between two equivalence classes is obtained by component-wise addition on the original concatenation operation. So it's the equivalence class that is formed from A concatenated with C and B concatenated with D. The identity element, which I'll call bracket O, 0 suggesting an identity, but that's purely a notational device. The definition is that it's the equivalence class that includes the pair AA. That is the difference between A and itself. The inverse of AB, of the equivalence class including the pair AB, is the reverse pair. That is, if we're thinking of a difference, we're just going to negate it and take the opposite order. And we define the ordering on this. We'll say that the equivalence class AB is at least as great as CD, provided that the AB pair concatenated with the inverse of the CD pair, which of course is equal to AB, this is equal to AB concatenated with DC, and that by the above definition is the equivalence class AOD, comma BOC. If that is in the positive part of the structure, then actually this is a strict ordering I'm defining here, because we're actually in the positive part of the structure. Now, there are a number of things that have to be shown about these definitions. The first thing that you always must show in a situation such as this, where we're dealing with equivalence classes, is that all of the concepts are well defined. There's a potential ambiguity here in that there is no unique pair of elements that characterize an equivalence class. By the very nature of the idea, there are a whole lot of different pairs that are grouped together in the equivalence class, so that the label AB for the equivalence class is replaceable by any other pair that satisfies the double squiggle relation. Now, you have to be careful in that situation that what you have defined is not dependent on the particular choice you have made for a representative from the equivalence class. And one has to go through each of these notions, the operation, the identity, the inverse, and the ordering, and establish that each one is well defined. This requires the use of many of the axioms to do that. Once that is done, the next step of the proof is to look at this operation on the set D and prove that that is in fact a commutative group with this as the identity element and this is the inverse of the pair of the equivalence class AB. This is a fairly straightforward step in the proof. The next step is to establish the Archimedean property, again fairly straightforward, and then the monotonicity. And at that point, one has all of the properties in this constructed system. One has all the properties of an Archimedean ordered group. Therefore, by Holder's theorem, it has an additive representation. Well, let me call one of those representations psi. It's into an additive representation into some subgroup of the additive reals. Then, having that representation, I must, from it, attempt to construct a representation for the original system of the closed extensive system. And the very natural definition is to assign to the element A the psi value of the equivalence class of 2A, that is A concatenated with A, comma A. If we're dealing with a different system, then 2A minus A amounts to A. So this seems like a very plausible definition. From it, one and the other properties one's established, one shows that the difference phi of A minus phi of B is in fact actually equal to psi of the equivalence class containing the AB pair. So that this really does look like a difference in this scale, which is what you would expect since we have attempted to construct a system of differences. From this, it's easy to prove that phi is order preserving, since if A is greater than or equal to B, the equivalence class containing AB is at least as great as the equivalence class of the identity, and that establishes this relation that psi of the AB pair is greater than or equal to 0. So that gets the order preserving character of phi. The additivity of phi rests on showing independently for the closed concatenation system that the operation O is in fact commutative. Then, if you know it's commutative, you know that you can write the equivalence class of 2AOB, comma AOB as this product. You see where it's coming in here is this product by definition, 2A, A, star, 2B, B, is equal by definition of star to 2A, O, 2B, AOB. Now the question is this equal to 2AOB? And that, as we ran into before, rests on having, as well as associativity, commutativity of O. So one has to prove that independently. Once that is done, then this step occurs. Since psi is additive in the operation star, this means this is additive. and that, of course, is the definition of phi of A, and that is the definition of phi of B, producing the additivity of the phi representation. So that's the general structure of this theorem that provides necessary and sufficient conditions for a closed extensive structure to be represented in the positive additive reals. Now, having that, one can begin to ask questions about how to improve the theorem. That is, or put another way, what's wrong with the theorem? Or what's wrong with it as a system of measurement? Presumably there's nothing wrong with it as a mathematical matter, but it may not be a satisfactory system of measurement for several reasons. One of these was discussed in connection with ordinal measurement, and the remarks here are not really different, and that is that empirically it may turn out that the indifference relation is in fact not transitive. In any empirical realization, it almost certainly will not be transitive, and there's a sense in which it has to be, the transitivity of it has to be viewed as an idealization. One, at least in physical situations, takes the position that were one able to provide sufficiently good equipment to make the qualitative measurements, one would find that it is indeed transitive. And in historical practice, improved methods of establishing the ordering have tended to take a system that showed intransitivities, and as you improved the methods, you lost them and only, in a certain sense, found them at a finer level of discriminability. This system has those potential difficulties. A second difficulty that is of very similar character is that the monotonicity property may fail to hold. One of the reasons would be, for instance, if I'm dealing, say, with the equal arm pan balance, and I start with an A and a B, and the pan, say, goes this way, and then I add a C on, something that's been established to be equivalent. The effect is to increase the total mass on both sides, therefore increase the pressure at this point and make the scale less sensitive. And so one might very well find, for instance, that A was, let us say, strictly greater than B, but then when I concatenated A with C and B with C, there's enough friction that this became an indifference. That kind of violation is to be expected. And again, I think the general feeling is that if one had ideal measurement conditions and sufficiently adequate equipment, one would find that this condition really didn't get violated. And certainly one doesn't expect to find a reverse. I mean, this sort of thing is almost certainly not going to occur. It's only the strict inequality may change into an indifference through the increased pressure. A third problem, and the one I want to concentrate on with the system, is that the assumed closure of the concatenation operation is an unrealistic assumption from several different points of view. One would like to study systems in which the operation is not closed for at least three quite distinct reasons. The first reason is that it is unrealistic in many, many physical situations to think that you can concatenate indefinitely. The various limitations of the laboratory are certainly going to prevent you from forming indefinite numbers of copies of any of the elements. Yet a closed operation implies that you can keep concatenating things with one another and produce something that runs off to infinity. And indeed, the proof of Holder's theorem very much rests on the ability to run off to positive infinity in order to form those limiting processes. That certainly is unrealistic. The second reason to be concerned about the concatenation is that you have systems such as that of probability that to a great extent look like extensive measurement systems, except for the fact that the operation is not closed. And let me be quite explicit about this. In the case of probability, we are dealing with events which can be thought of as subsets of a collection of sets. And one of the properties of probability, and we're going to go into this in some detail in the lectures on probability, but one of the properties is that if capital A and capital B are events, and A intersect B is disjoint, then the probability of A union B is the probability of A plus the probability of B. This is the well-known additivity property of probability. And you see that you have additivity, but you don't have additivity for an arbitrary union of events. It's only for the union of disjoint events. So we're here in a situation where if you think of union as the concatenation operation, which is the natural thing to do, it is not defined for every pair. That is, you're only interested in concatenating the disjoint ones, at least as far as getting an additive representation. Now, if one thinks that probability is to be reducible to a theory of extensive measurement, it's clear then that one has got to have a theory that concerns a non-closed operation. The third motive for studying an operation that is not closed is that in the theory of conjoint measurement, that is the theory that is concerned with orderings of a Cartesian product of two sets, the method of proof is to try and reduce the problem to one of extensive measurement through inducing an operation on one of the components. We'll go into that in considerable detail, but let me say at the moment that when you go to do that in a realistic system of conjoint measurement, you wind up defining an operation that is, again, not closed. It is not defined for every pair of elements. And you would not be able to pursue that line of proof unless you had a theory for extensive measurement with a non-closed operation. So with those three reasons behind us, we must now turn to what happens when you relax the closure operation. Once we begin to consider systems that do not have closed operations, or what we will call partial operations, several issues that arise that have not previously been a problem. First of all, we've got to characterize in some fashion the sets of pairs of elements that can be concatenated. That can be done notationally simply by describing or listing all of the pairs for which the concatenation operation is acceptable. That is, defines a subset I'll call B of the set A of objects. There'll be a set B, which is a binary relation on A, that is a subset of A cross A, and it lists the elements for which the concatenation is a possibility. And then the concatenation, of course, is simply a function from B into A. So our structure now will have A, the ordering, the relation B, and the concatenation operation defined from B into A. The second concern that arises is the possibility that the system has a maximal element in it. That couldn't arise in the previous systems where you had an indefinite amount of concatenation of positive elements. It had to go off to infinity. There could be no maximum. But the minute you have a partial operation, maxima can occur, and we're going to have to be a little bit careful about them. And in particular, we're going to exclude one kind of maximum that is defined over here, definition 3.4. I'll say that an element Z of A, it's an element of A, is an essential maximum in A if and only if, first of all, Z is a maximum element, that is, Z is at least as large as A for every A in capital A, and secondly, for some element A in the structure, Z can be concatenated with it. Now notice that if Z is concatenated with A, since Z is a maximal element, and we're dealing with a structure that, for the most part, except for the maximal element, is positive, the only real possibility is for Z concatenated with A to produce itself Z. Is this a realistic thing to be concerned about? Well, we know of at least two very important examples of structures that have essential maxima. The first of these is any probability structure where the universal event is going to be a maximum element, that is, the probability of the universal event, call it X, is 1, and it is greater than or equal to the probability of any other element in the system. So it's a maximal element, and it is, in general, going to be essential in that one can concatenate it with something else, namely, if concatenation is the union operation, one can concatenate it with the null event. So that in that structure, one has to worry about maximal elements. In another structure arising in the theory of relativity, the concatenation of velocities entails a maximal element, namely the velocity of light. And the velocity of light concatenated with any other velocity produces, again, the velocity of light. So this is not an idle matter. On the other hand, in the structure we're going to talk about, I'm going to simply exclude the notion of an essential maximum. That does not preclude, however, the possibility of an element in the system that is maximal and cannot be concatenated with anything else. And we have to be a little bit careful about such an element, as you'll see in the statement of one of the theorems. All right, now what we must do is, as before, characterize the behavior of the ordering, the operation, and now, of course, we have to worry about the domain of the operation, the set B. That, too, must be characterized. And it's intuitively reasonably clear that B cannot be too sparse. That is, if the operation, the existence of the operation is to have any bite in holding down what order preserving mappings will do, the set B on which it's defined has to be sufficiently rich in the whole structure as to cause some constraints. If, for instance, B consisted of just one pair of elements, and there's nothing at the moment that would exclude that possibility, then the operation would be only defined for that pair of elements, and that would provide very little constraint on the system. It may prohibit some monotonic transformations, so that it's not completely an ordinal scale, but it's not going to exclude very many things. So we must somehow build in some richness. Now, one consequence of doing this is that we're no longer going to arrive at necessary and sufficient conditions for a representation. we are going to be imposing constraints on the system that are much stronger than those that are imposed just by the existence of an additive representation. So the theorem will not, in some sense, be as satisfactory as the one with the closed operation. Or looked at another way, the original theorem was highly restrictive. If the notion of a closed operation had not been in this part of the hypotheses of the theorem, but had been listed as an explicit axiom, then the closure of the operation would indeed have been restrictive, much beyond the order-preserving and additive aspects of the representation. Given we're working with a partial operation, that restrictive nature becomes very apparent in the nature of the theorem. Now let us look at the axioms that have been proposed for what is called an extensive structure with no essential maximum. As before, the ordering is a weak ordering, and the operation satisfies weak associativity. On the other hand, here I must conditionalize it on the assumption that if BC is in B and A, comma, BOC is in B, and so on the same thing on the right-hand side. I have to assume that all of these concatenations exist, but if they exist, then weak associativity holds. The next two conditions are of quite a different character than what we've seen before. These are what are called structural axioms. They don't follow from the representation we're interested in. They are restrictive. There are other systems not satisfying these that can have an additive representation. The first of these is a constraint on B, and in fact it buries together two things that might better have been separated, although this is the way it's presented in the Foundations of Measurement. The first is the assertion that if A is concatenated with C, that is, if A can be concatenated with C, and A is at least as large as B qualitatively, then C can be concatenated with B, and the monotonicity property is stated as AOC is at least as large as COB. Now we're, in a way, bringing in commutivity of the operation by this funny indirect method of reversing the order here. But the important thing, that's all very technical, but the important thing here to understand is that we're saying that if we can concatenate A and C, and if we deal with something that is smaller than one of the components, then that can be concatenated with the other side. And so it's a structure that if you know the two things can be concatenated, then things that are below them in the ordering will be concatenated. That's a very restrictive requirement on the set B, but it is one that ensures that there will be a sufficient richness of the operation. The second requirement that we're going to impose is one that's ensuring that there are an adequate number of elements in the whole system to work with. Basically, the intuition that's involved behind this assumption, that I'll state explicitly in a minute, is that we want to be able to produce small elements in the system. Recall that in the proof of Hölder's theorem and therefore of the closed extensive structure, what we did was run off copies of things to infinity and compare how many copies of one large number of copies of something matched another. But here in a system where we may very well have maximal elements and we're not permitted to concatenate indefinitely, we're going to have to follow a different route. Namely, we're going to have to look for very small elements and then build up from them using the limiting process by essentially going down to things that are very near zero. that is ensured, the possibility of that is ensured by this axiom, which says that if A is larger than B, then I can always find an element D in the set A, such that B can be concatenated with D, and that B, when it is concatenated with D, does not exceed A. That is, there's something sufficiently small to fit in the difference between A and B. It doesn't have to fit it exactly, but it will fit within that difference, and that gives us the small elements that we need. The fifth axiom is positivity. It's, as before, it says that if A and B can be concatenated, then AOB is strictly larger than A. Now, when we come to deal with the Archimedean axiom, we have to go about things a little differently than before. Not much, but there's a little concern. And that concern arises from the fact, of course, that n copies of something may or may not exist. Since the operation is not closed, you cannot be sure that n copies of something will exist. So that, for instance, if I were to try and state the axiom that given that B is greater than A, there exists an integer n such that n copies of A is greater than B, which is the standard classical way of phrasing the Archimedean property, we may get in trouble because we may run out of the ability to make the copies of A and then fail the axiom, not because it's deeply violated in the structure, but because we're simply not able to make those concatenations. So we have to go at it in a somewhat different way. And the following technique seems to work very well. We will define a standard sequence of the system. It's a sequence of elements A sub n, where n runs through some integers, not necessarily to infinity. This may be a finite sequence. It's called a standard sequence if for each n for which the an exists, then the previous one, an minus 1, and the first one, a1, can be concatenated, and their concatenation is indifferent to the nth one. So it's like the sequence that is generated by n copies. This is the inductive definition of n copies. Now, standard sequences are really very important. I mentioned up here two examples of standard sequences that one uses in ordinary everyday measurement. The case of a ruler is indeed a standard sequence in which the units are whatever it is. Let's say it's marked in millimeters. It's a standard sequence of multiple copies of millimeters. The standard weights used in a weighing scale, again, are integral multiples of some unitary weight. So this is not only a theoretical construct of some importance, it is indeed a practical one. Now, the Archimedean axiom gets defined in terms of standard sequences by saying that every strictly bounded standard sequence, and by that I mean there is an element B that is larger than each of the A sub n's for all of the n's for which it's defined. And the assertion is then any such strictly bounded standard sequence is finite. There is no way that you are going to have an indefinite number, an infinite number of copies of n that stay beneath a particular element B. So those are the 6 axioms of an extensive structure with no essential maximum. The positivity requirement rules out the essential maximum, you see. As I pointed out before, if you have an essential maximum, you violate the positivity property. And so by putting it in, you completely prohibit an essential maximum from occurring. Now, the theorem that is proved, theorem 3.3, has as its representation that if A is an extensive structure with no essential maximum, then there exists a homomorphism into the additive positive reals. That is, I'll say it once again, it's order preserving, and if A and B can be concatenated, phi of AOB is the sum of phi of A and phi of B. The uniqueness is slightly different, and it harks back to this problem of the existence of an isolated maximum, not an essential one. It says that if phi and phi prime are two homomorphisms into the additive positive reals, that is equivalent to the existence of a positive constant such that for all non-maximal elements, phi prime, non-maximal elements little a, phi prime of little a is equal to alpha times phi of a. What happens at a non-essential maximal element is essentially free. You can give it any number above all the other numbers that are being used, and there's nothing to tie it together. So that the result is in other words, if you throw out the non-essential maxima, then it reduces to the usual concept of a ratio scale. Now, once again, you can ask the question, are the axioms independent? And that's discussed on page 86. And once again, a small error has been made in those examples, and the third one should be replaced by this example. It's the positive rationals. It's ordered by greater than or equal to, and the operation is in fact closed, and it is defined to be A plus 2B. And that axiom manages to violate this third condition and satisfies all the others. So the axioms are once again independent. Now there's considerable room for potential modifications of the system. One can change these structural axioms and quite possibly provide something that is weaker and get the same fundamental theorem. Often, it is necessary when you further weaken structural axioms, it is often necessary to compensate that weakening by adding more conditions that are necessary under the representation. There are many, many statements that are necessary that we're not explicitly stating here in the form of the axioms. And sometimes, and we'll see a good example of this when we get to conjoint measurement, sometimes you can weaken structural axioms at the price of introducing several more of the necessary conditions, the ones that follow from the representation, and are axioms that are subject usually to empirical verification. You see, one of the things that is generally true of the structural axioms is that you really can't verify them empirically. You can try to convince yourself that an empirical context has these properties, but it's usually not very easy to carry out any direct verification of them. Particularly something like a solvability condition is hard to know how to verify it. Whereas things like associativity and weak order are relatively straightforward to try and verify, at least for finite data samples. As I mentioned before, the Archimedean axiom is one that one can never verify, even though it is a necessary property of the representation. It has to do with in a deep way with the fact that you're going into the real number system. The fact is that no finite set of data is capable ever of rejecting or verifying the Archimedean condition. Now, the proof of this theorem is not really very easy. It's quite lengthy. I want to talk a little bit about the general strategy of the proof, but for the full details of it, you should go to the theorem proved in Chapter 2 on pages 46 to 52. It's a fairly fussy proof, and it's far more complicated than one can present in a lecture. But let me try to indicate sort of the strategy that's involved. Suppose B is an element larger than A, then define n of AB to be the largest positive integer such that n copies of A exist and B is still larger than n minus 1 copies of A. Now, what one does is to establish the existence of a sequence, the descending sequence of elements A1, A2, AM, such that for every element B in the structure, if one goes out far enough on that sequence, that is, if you go to sufficiently large M, you can find the existence of an integer NAM comma B. And moreover, that integer, once you get out far enough, is increasing to infinity as the index M goes to infinity. Intuitively, what you're doing in this sequence is finding smaller and smaller elements and then saying to yourself, here think of this as the structure, and you're getting a system of elements that goes increasingly, let me draw it the other way. I'm aiming towards what amounts to a hypothetical 0 down here. So I have an A1, and I get a sequence like this, and it keeps going down here. And then I take an element B, say here, and what I want to do is I'll go down here and I'll find an AM, and then I'll see how many copies of that I can make before I get to B. And then I will keep going down finer and finer, and the trick in the proof is to show that you can in fact do that you can go down there, and that the number of copies that you are able to make is going off to infinity as the number of elements increases down towards this hypothetical 0. Then you show, once you've got this sequence and these numbers, you show that the ratio of the number of copies of AM to approximate B is what it amounts to, and the number of copies of AM to approximate a different element C, that ratio as M goes to infinity exists. And moreover, that ratio is in fact independent of the detail sequence that's chosen. And that ratio becomes then really the definition of the ratio of phi of B to phi of C. And then the problem is, of course, to show that has the order preserving and additive properties. And the arguments are not very different, although they're somewhat more subtle, but they're in principle not very different from the ones that were used in establishing the order preserving and additive properties of the closed structure. What you're doing, you see, is basically the same kind of idea, in that by going down through this sequence, you're then able to say how B, and let's say here's a C, how they relate to one another in terms of how many copies of one of these very small elements it takes to get to B and how many copies it takes to get to C, which is what you're studying in that limit. And so it's a kind of an artifice to take advantage of the fact that you can go get to very small elements instead of the artifice or the trick that was used in Holder's theorem, which was to run everything up to very large elements and then make the comparisons up there. So that's the general strategy of proving this theorem, which theorem 3.3, the third theorem in Chapter 3, which is due really to the authors of the Foundations of Measurement, although it is related to a number of other theorems that are in the literature, and those relations are discussed in the text.